welcome to Lesson 9 of our Beginning C course. And in this lesson, we're going to talk about one of the more advanced topics within learning C, and that's our dynamic memory allocation. So basically, let's look at a basic C program to kind of understand what we're going to be looking at today. So essentially, most variables that you declare are statically allocated, basically meaning that the compiler has to know how much memory to allocate when you compile the program. So when you declare a variable or an array like this, you have to put a static value in your sort of array declaration here. You can't have this number change if you need more memory or shrink if you need less memory. So basically what we're going to look at today is a way that you can dynamically allocate memory within your program so that if you need more memory, you can create it at runtime. Because basically these arrays that you declare statically, the compiler sets up the amount of memory that you need, that way you can store sort of the information that you need in them. But that information, that memory, you don't have direct access to within your program. You can simply sort of write values to it, read from it, but you can't add more memory to a particular variable. And to do that, we're going to use pointers and a few functions that are in the C standard library. So we're going to need to include stdlib.h. So the basic way that we allocate new memory works with pointers. So let's take a look at a simple example of how we would do that. So to declare this same array dynamically, we would use the memory allocation function that's defined in the standard library, like this. First, we change this to a pointer. And then we set that pointer to point to the new memory that we're going to allocate at runtime. So the memory allocation function sets up the new memory that we're going to use and returns to us a pointer to that memory location. And basically we're going to set our integer here to point to that new memory that we're going to allocate. The function takes one parameter, and that's how much memory we're going to allocate. And since we want space for an array of 100 integers, we're going to use 100 times the size of a single integer as the size for how much memory we're going to allocate. In order to get the size of a single integer, we have this size of function in C. We multiply by 100. And now we have the same or a similar array that we had before, but that memory has been dynamically allocated. So if we had a program where we wanted user input to allocate space for more data, we could do it with memory allocation here. So now we can actually set and read values in that array the same way that we would before. One thing that's important to note, and you might get a compiler warning about this, is that the return type of memory allocate here is actually void. And so what a lot of times that you might need to do is to convert the output of this function into whatever type that you're trying to store it in. So it returns to you memory with no particular type, and you can convert whatever you need like this. You can cast is what it's called. To get memory of type integer in this case, you just simply change the function call to look like this. But depending on what compiler you're using, you may not need this explicit conversion. You might just get a warning. So we can compile and run this. And as you can see, the array basically behaves in the same way that it would before if we had statically declared it. So dynamic memory allocation is just a way to sort of set up new memory at runtime that we can access. And we can use this, say, for instance, if we had a case where we wanted to continue adding values to an array, but we didn't know how many values. Let's say it was dependent on user input. We could allow the user to enter as many values as we wanted to. We could use dynamic memory allocation to continue allowing the user to enter values and storing them. So what we're going to implement in order to get a better look at dynamic memory allocation and data structures actually is we're going to create a linked list, which is a data structure that will allow us to add an arbitrary amount of elements. So we can keep adding new items to this array that we'll have, or the list that we'll have, without having to declare a new array like we might if we were using statically declared memory. So let's get started working on that. So before we get into actually coding the linked lists, let's just talk a little bit about what we're going to be building. So essentially the way the linked list works in order to allow us to add an arbitrary number of elements is we start with a top element, something that we hold at the top of the list, and that contains a pointer to the next element in the list, and each successive element will contain a pointer to the next element in the list. So if we want to access an individual item, we're going to have to look through, starting from the top of the list, in order to get the particular item that we're looking for. So access won't quite be as fast. In order to get an individual element out of our linked list, we're going to have to look through as many elements as we have in the list before it. So now we can get started with the data structures we're going to need for our linked list. So to get started, we can have two structures, one for the list itself and the other for the actual nodes that will contain the data. So first we'll have an integer value to hold the data that we'll actually put in our list, and one pointer to the next node. So basically this will allow us to access the next element in the list from an individual node. So our node will be a structure that contains one element of data and one pointer to the next element in the list. So then our list and actually the only thing that we need to hold in our list itself is the top. So let's call this the head pointer. So this will be the basis of our data structure. In order to add something to the list, we're going to need to create a function called pushList. It'll take our list as a parameter and whatever value we want to add. So the first thing we need to handle is if our list is completely empty, what do we do? And if we're trying to insert into an empty list, we set the first element in the list, the top of the list, to be the element that we're inserting. So we can tell if our list is empty by telling if our head pointer is pointing to nothing or null. So in order to access members of a particular pointer, we can use this sort of arrow notation here. So instead of having to dereference a pointer and attempt to access an individual member of that dereference, we can use this shortcut to dereference the pointer and get a particular member of it if it's a structure. So we're going to do this to check if the list is completely empty. And then we're going to create a new node. And we're going to need to allocate new memory for that node, since it's going to be a new data object. So now that we've allocated new memory for the node, we need to set its value. Yeah, this node needs to be a pointer so we can assign it to the new memory location. So we assign the new node the value that we're adding, and then we set the top of our list to be this new node. So the other case is a little more complicated. We need to figure out what to do if we do have a top of the list. We need to figure out where we need to insert our new node. And how we can do that is obviously at the end of all of our existing nodes. So we need to loop through all of our existing nodes and figure out once we reach the end. And that's where we're going to put our new node. So we'll create a temporary node to use to check to figure out if we're at the end of our list or not. You can just call that tNode. And we're going to set it to the top of our list. And then we can use a while loop to figure out when we've reached the end of our list. So all we need to do is loop until the next element of our temporary node is null. That means we're at the end of the list. So we're basically implementing this as a positive condition so that we keep looping until the next node is null. And we can move through our nodes like this. Well, since tNode is just a pointer, we can just set it to be the next node each time we iterate. So each time we go through this loop, we'll move one more element forward in the list. And when we hit the end, tNode will be pointing to the last node in our list. And so this is important because we're going to need to set the next pointer of the last node in our list to the new node that we're about to create, holding the data value. And here we can basically use the same code as above. We create a new node, assign the value, but this time we set our temporary node.next value to be our new node. So that should basically be all we need in order to add nodes to this list. We iterate through all of the nodes that we have until we get to the end. Once we get to the end, we create our new node, assign it our new value, and set our temporary node's next value to our new node. And remember, our temporary node will point to the same memory location as the actual list, since we're starting with the head pointer. So now that we can actually add elements to the list, let's take a look at how we can print all of our elements out so we can see what's actually in there. We can write a new function for this that also takes a list. And we can basically kind of use a similar loop as before. Create a temporary node, set it to the first element in our list, and iterate from there. However, this time we're not going to check if the next element is null. We're only going to check if the element that we're currently looking at is null, because we want to print out every node in the list, including the last one. So if we were only checking for the next one, we'd miss printing a single node. So let's go through every element in the list and print out its value. Then we can continue the loop. So that's actually all we're going to need to do to print out all of the nodes that we have in a particular list. So now we can, in our main function, create a new list, add as many nodes as we want, and print them all out to make sure this thing works. And let's just initialize this to null. We can do that like this. And then we can push some values to our list by using its reference. And then we can print out all the values that we've stored. So now we can make and run this and make sure our linked list is working properly. So as you can see, when we called the print nodes function, everything that we stored in our linked list was appropriately printed out. So basically the dynamic memory allocation here allows us to have an arbitrary amount of values and sort of create and store things in memory as we need. We don't have to know exactly how many things we're going to store in a particular location before we start writing our program. So just to kind of summarize what the functions that we've been using do. The memory allocate function allows us to grab a block of our existing memory. The memory that we do have works kind of like an array, and we can grab a specific block of it to set some new specific variables in there to store our data, basically. So our memory allocate function here allows us to get a specific size of that memory that we have available to us while our programming is running, as opposed to having the compiler set up that memory for us. So once we have that memory, we can assign it to a type or a variable within our program, and then we can manipulate it directly like we would any other value in our program. So that's essentially an overview of the basics of dynamic memory allocation. It's a concept that we're going to continue to use throughout this course. And that's it.